Guys, hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. Today we're going to look at the basic concept of pressure. And of course, we have mentioned the concept of pressure in one way or another in various discussions on the concept of entropy, enthalpy, and other related areas under the concept of chemical thermodynamics. Now, in this particular case, we're going to look at pressure from the basic level. And of course, we have been mentioning this particular concept of pressure as a ratio between the force and the area of application, and we're going to give it in terms of pressure equals to force over area. Now we can have this one in terms of an algebraic representation, whereby we're going to have P to represent pressure, which is equivalent to force over area, where F represent force and A represent area in that specific order. So in this case, I'd like to be requesting our members to begin on the specific dimension that we're going to give these particular variables. And in this case, we said that force is given in terms of newtons, and we're going to give area in terms of the square of meters given as such. So therefore, one of the units that we're going to encounter in trying to describe this aspect of pressure is given in terms of Newton per meter square given as such. So therefore, I'm going to give at the end of this specific discussion different units that we can assign to this aspect of pressure whenever it's going to be used in different circumstances, as I'm going to mention. So in this case, force basically is that which causes change in the motion of a body that is free to move. And from the study in classical mechanics, we said that the various aspects of Newton's laws of motion describe the aspect of force. And we said that in case we have a body that is static, a force can be applied and in order to cause this particular body to move or change direction. Therefore, this particular aspect of a force we're going to see can be described in various ways, but concerning pressure, basically it's going to be giving us a ratio between the force and area to give us this aspect of pressure. Now, in this specific discussion, we're going to concentrate on the aspect of atmospheric pressure. And basically, at the end of our discussion, we're going to see how we can, at a basic level, try to quantify this aspect of pressure using a simple instrument. So in this case, I'm going to mention this using this specific illustration, whereby we're going to have a simple illustration that is assisting us try to quantify this aspect of pressure. Now, atmospheric pressure is measured using an instrument referred to as a barometer, and this basically is going to be given as a mercury barometer. So this barometer consists of a simple illustration that I'm giving on the board, whereby this particular container consists of mercury, and then we have this one given as a column that is in form of a tube. And then we're going to have these specific arrows indicating the atmospheric pressure acting on the surface of this particular mercury. So this simple illustration constitutes what we refer to as a mercury barometer. And this barometer is going to be having this specific column indicated in terms of millimeters. So therefore, whatever atmospheric pressure is acting on the surface of this specific mercury, we're going to have this height of the column varying depending on the degree of pressure that is applied. So more pressure indicates that there's going to be a rise in the column of this particular mercury, and then less pressure, there's going to be a relief, and then there's going to be a drop in this specific aspect of that particular mercury. Now, there's a relationship between the height that is going to be realized from this particular column and the pressure of mercury or the atmospheric pressure experienced at the bottom of this particular area. So now, in terms of dimension, we're going to consider the base area, which is going to be given as A, which is basically the cross-sectional area of that particular column that we're going to consider, and then the height, which is going to be indicated in terms of h in terms of millimeters. So therefore, we're going to have this dimension indicated in terms of millimeters of mercury. And the pressure of the atmospheric pressure, therefore, can be given a relationship from this specific pressure at the bottom of the column. Therefore, we can give pressure at the bottom of this specific column using the relationship of weight of the column. So this is going to be the weight of the mercury column divided by the cross-sectional area at the bottom of this column. I'm just going to give it in terms of that summary. So if you consider the weight of the mercury column and the cross-sectional area at the bottom, we're going to see that this one is basically proportional to the mass of the mercury. So the relationship on my right of this specific equation is proportional to the mass of the mercury all over the cross-sectional area at the bottom of this specific column. And therefore we can expand this relationship still for the pressure at the bottom of this column by having this one. So from our study on the concept of mass, we said that we can obtain mass of a substance by finding the product of its volume and density, especially when we're dealing with the concept of a liquid such as the mercury liquid that we're having in this case. So we shall have mass given in terms of the volume of mercury times the density still of mercury, and then this over the cross-sectional area at the bottom of this specific column, as I have said. And this is going to give us a proportionality whereby we are going to have a volume still expressed in terms of the cross-sectional area and of this specific bottom times the height. So basically from the study of regular figures, we said that we can find the volume of a cylinder by finding the cross-sectional area times the height. So therefore I'm going to employ the same concept in finding the volume of mercury by multiplying the cross-sectional area given as such times the height and then times the density. Now this density can be given in terms of rho given as such. So I'm going to use that symbol because of our space in order to have that one over the cross-sectional area given as such. So from our numerator and denominator, we're having a common factor of cross-sectional area. Therefore, we're going to have this one implying the height times the density, giving us proportionality to the pressure at the bottom of this specific mercury column. So we can be able to derive the relationship of between the pressure at the bottom of the mercury column using the relationship between the height and the density of this specific mercury column. So from this specific discussion, then therefore we're going to develop various ways in which we can give pressure in terms of this algebraic representation. Now I've said that basically we have developed the relationship between pressure using the height and the density of this specific mercury column, and therefore we're going to see that there are some specific constants that we're going to modify or rather include in this particular relationship so that they can assist us come up with various aspects of pressure in various contexts that we're going to use this particular of course concept of pressure. So I've said in some areas like as I've said and the thermodynamic variables of temperature and volume and other areas that we're going to see. So lastly, I promise that I'm going to give the specific units that we're going to use as we come by this aspect of pressure, whereby we're going to have one of the units referred to as a Pascal, and this is going to be initialized using PA given as such, and this is equivalent to 1 Newton per meter square given as such. So that's one of the units that we're going to use in measuring pressure, and then we're going to have 1 atmosphere equivalent to 760 millimeters of mercury, just as we have indicated in this. So the rise in millimeters of the height of this specific column of mercury is going to give an indication of a 760 measurement is equivalent to 1 atmosphere given as such. So in some text we are going to have this one given as in terms of torrs. So this is going to be 760 torrs equivalent to 1 atmosphere given as such. And lastly, we're going to see that we can give a conversion between pascals and atmosphere in terms of 1 atmosphere equivalent to 101, and then we're going to have 325 pascals given as such. So these are some of the terms or the conversion we're going to use for measuring pressure, and I hope that they are going to be of assistance to us as we come across various topics of application for pressure. So that is it for now, guys. Bye. God bless you. Catch us in our next video.